Welcome to section 7.6. This is called linear programming. This is the last section that we're going to be doing in chapter 7, and so this kind of ties everything that we've done together. But take a look. We're going to be looking at a system of inequalities. So we did inequalities in 7.5. Now we're going to put multiple ones together. And I would suggest that you have multiple colors for this section like we did for 7.5. And so we want to figure out the region that's given by this system. So here's what I'm going to do. I'm going to start with some really light colors, and I'm going to try and minimize as much as I can. Okay, I'm going to start with this x equals 0, or x is greater than or equal to 0, because we're looking at, I'm going to try and make this as clear as I can. So I'm going to go multiple colors. Okay, if x is greater than or equal to 0, we're talking at equal to is this line right here. And I can have anything I want greater than or equal to 0. And it even comes down this way. Okay? So I'm going to switch my colors again. Let's go a green. And I'm going to do y is greater than or equal to 0. And so this is the y equals 0 line. And if we're going greater than or equal to 0, I can have anything up here. I'm going to try and minimize as much of this messiness as we can. Okay, let's go a little bit darker. Let's pick like a blue color. And I'm going to do this first equation, and I'm going to solve for y. And so I'm going to simplify this. If y is less than or equal to negative x plus 9. Okay, and so that's there. Now, I'm going to draw my picture. My y-intercept is at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And my slope says negative 1. So down 1 over 1. I'm going to try to make this as clear as I can. And I'm looking at now this line right here. And the question is which way to shade. And we said let's pick the point 0, 0. So is 0 less than or equal to 9? The answer is yes. So I shade towards 0, 0. So I'm looking at that region. Let's go one more color for our last one. And if I solve this, I have negative y is less than or equal to negative x plus 3. When I divide by negative 1, don't forget with inequalities my sign switches. So y is greater than or equal to x minus 3. So minus 3 is like way down here. I'm going to pick a nice point I know is 3, 0 though. And then I'm going to go, my slope is up 1 over 1 from there. So I'm just trying to kind of work my way around the fact that my graph is not that great. It's a solid line on all of these again because they're or equal to. If I pick 0, 0 again, is 0 greater than or equal to negative 3? The answer is yes. So I shade towards 0, 0. Okay, so in this whole mess, let me try and get as dark as I can here. We have to put our region and kind of show where it is. Well, okay, I know I started at the point 0, 0 and I got here to this point 3, 0. And then it looks like it went up here and then it followed this line to this point and then came down straight. And so this is what we call a feasible region, and this is a feasible region, and that just means this is the region where my solution set occurs. Okay, so my solution set is all of that area. And this is a bounded region, and that's important. Bounded means that there's no, you get a stopping point. It's an enclosed region. Now, we want to find the maximum value of z, and z is what the idea of a program is. I'm going to give you this program where z is 3x plus 2y, and one of the points, the solution, has to come from your solution set above. And so what we're going to do is we're going to deal with points within that region. And so, like, let's pick a point. How about the point 1, 1? So if I'm looking at the point 1, 1, I plug it into z, where z equals 3 times 1 plus 2 times 1. 3 plus 2 is 5, so z is 5. Let's pick another point in my region. How about the point 2, 3? So if I do 3 times 2 plus 2 times 3, I get 6 and 6, which makes 12. One more point. How about the point 3, 4? So 3 times 3 plus 2 times 4, 9 and 8 make 17. And so what I can do is find these are all solutions to my system of inequalities, and these are just general solutions. Now we want to know what's a maximum to my system, a maximum to my program that they give us for my z. In order to find a maximum, here's what's important. It has to occur at a vertex. And a vertex are those nice points. So one vertex that we have is the point 0, 0. One vertex is 3, 0. Another vertex is 6, 3. And the final vertex is 0, 9. And so these are vertices of our bounded region. And so what we're going to do is test these vertices by using our program z equals 3x plus 2y. Okay, so let's start with the point 0, 0. If I plug that in, you get 0. At the point 0, 9, if I plug that in, 3 times 0, 0, 2 times 9 makes 18. I have the point 3, 0. Okay, so 3 times 3 is 9 plus 0, so we just get 9. And I also have one last vertex, which is the point 6, 3. 3 times 6 is 18. Plus 2 times 3 is 6. 18 and 6 makes 24. And so as I look at this, the question is which vertex gives me a maximum? And in this case, the maximum value occurs at the vertex 6, 3. And so what we are doing today, and this kind of gives you a general overview of what's going on. What we're doing today is we're going to find a region of intersection called the feasible region. And then we're going to use a program, a value of z, to figure out where our maximums or minimums occur. And so that's kind of the idea. So let's scroll down. And we're going to use our program from above, but the process of finding a minimum or a maximum, we call this optimization. Optimization, and we're trying to optimize the value of z. Whether it be a maximum or a minimum depends on whatever situation we're working with. Okay, we are going to, the quantity to be maximized is called our objective function, and our objective function is that function of z. And that's what they're talking about in this program is can you maximize or optimize the value of z. The linear inequalities are what we call our constraints, and they're limiting which areas we're looking for in order to optimize our program. And so this is the idea. We found that the maximum point above for our program was the point 6, 3. Can we find the minimum? Well, sure. We already went through and plugged in the points, our vertices, into our program, or into our objective function. I'll use that word for a little bit. And so what we found was that the minimum value occurs at the point 0, 0. Okay? So here again are things to keep in mind. First of all, if they are bounded, so if a region is bounded, let me give you a few little side notes. If a region is bounded, then your max and your min will occur at vertices. Okay? So that's the biggest thing. The second thing, if you have an unbounded region, which we're going to show you in a sec, which means that you don't have all sides of this region, it's not enclosed, then if a solution exists, if a max or min exists at a vertex, okay? And if it's unbounded, you won't have a maximum and a minimum, you will just have one of the two. And again, it completely depends on the situation, but this is kind of the idea. It depends whether the region is bounded or not as to whether maximum or minimums occur. So let's keep going. Let's show you some examples. All right, let me get some better colors, shall we? I'm going to look at, this gives us multiple regions now. So I may actually, because these are still the same, we just know that this whole region is a possibility. So I'm just going to use one color for these two, only because I just don't want to make this as crazy as it could be. So that's those two. Okay, so let's go to green. I'm going to take each of these equations and I'm just going to solve for y. So my first equation, if I rewrite this, is going to be y is greater than or equal to -1/2 x plus 2. All right, so let's graph this first. Plus 2, down 1 over 2, down 1 over 2, down 1 over 2. Anyways, you get something that looks like this. Okay, if we test the point 0, 0, we're saying is 0 greater than or equal to 2? The answer is no, so we're going to shade away from 0, 0. All right, let's keep going around our circle. If we do our next equation and we solve this for y, you get that y is greater than or equal to -3x plus 7. Okay, so up 2, 4, 6, 7, down 3 over 1, down 3 over 1, down 3 over 1. Anyways, you end up getting this line. And again, we're going to plug in 0. Is 0 greater than or equal to 7? The answer is no, so we again are shading away. All right, let's go last one. If I solve my equation for y, now you can do the work if you need. I'm just going to shorthand this a second. Y is less than or equal to 1/2 x plus 7/2, or 3.5 if you want it. Okay, so let's look at this. 1, 2, 3.5, up 1 over 2, up 1 over 2, and we kind of get this line. And again, we're going to check 0, 0. Is 0 less than or equal to 7/2? The answer is absolutely yes. So we shade down here. Okay, I'm going to pick bright red this time, and let's figure out where our region of intersection is, or our feasible region. And I'm going to try and look and see what I can find. I know this has got to be a stopping point. Okay. And if I can kind of see this, it looks like it's kind of coming up here. So I have a vertex here, and I have a vertex here, and we can't forget this blue line. So we have a vertex here. And it has to be under the purple line, so it's got to go like this, which means all of this in here is going to be my feasible region. So we're looking at the feasible region in red. Now they're asking you for a maximum value. So let's talk about this idea of the maximum. First of all, we have an unbounded region. And if you have an unbounded region, you are either going to have a maximum or a minimum. And so if we kind of look at this, let's just talk about the vertices we have so far. We know that we have vertices at these following points: 1, 4, 2, 1, and 3.5, 0. And again, I was trying to get as close as I can, but we're, okay, so taking a look at this. Now, if I plug these in, if I find z values for each, let's start with the first one. This is the point 1, 4, 2, 1, 3.50. Okay, if I do the first one, at 1, 4, my z value is 12. At the point 2, 1, my z value is 10. And at the point 3.5, 0, my z is 14. Now, as I look at this, I know that a maximum and a minimum have to occur at vertices. Okay, so here I can see automatically is my minimum, but let's talk about my maximum. Because my minimum occurs, that means I have no maximum. And let's talk about why. The problem is this goes out forever and ever, and this goes out forever and ever. There are bigger and bigger and bigger values of x and y that could create a maximum that might be way out here and beyond. And so as I look at this, I know here's one of these three has to be my minimum, and we end up finding it's this value right here, but my maximum, because it's unbounded, cannot be found. Okay, and so that's kind of the idea. You want to look at this picture and you want to say, basically, I can't have a maximum because I can keep getting bigger and bigger and bigger points up here for x and y that are going to make this a maximum. And I just don't know what that point is because it keeps going on forever and ever and ever. Okay, and so this is the first idea. The second thing that we have is just a story problem. This story problem is going to take us a little bit of time, but again, you're going to want some multiple colors. So let me slide this down. And I'm actually going to go to some lighter colors again. And I'm going to start here in the middle because I want to write out what I find first, and then we'll start looking at things. All right, here we go. Let's read through this. A liquid portion of a diet is to provide at least 300 calories, 36 units of vitamin A, 90 units of vitamin C. Dietary drink X costs 12 cents and provides 60 calories, 12 vitamin A's, and 10 vitamin C. Dietary drink Y costs 15 cents and provides 60 calories, 6 vitamin A's, and 30 vitamin C's. How many cups of each drink should be consumed each day to obtain an optimal cost? I'm going to circle that for a minute, and still meet its requirements. Okay, optimal cost means that's what we are optimizing, so that's our objective function. Because they're talking about cost, we're going to use cost as our objective function. Now, we look back in our problem and we see it costs 12 cents for X and 15 cents for Y. Those are the only two things in cost, and so that's why we're using them as our objective function. Now let's talk about constraints. All right, so we're going to have some constraints. Let's talk about drink X. Is there anything in terms of the amount of drink X that you can't have? Well, let's be honest. You can't have negative units or negative portions of a drink. And so when we talk about our constraints, we want to first start with that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. You can't have negative portions of a drink. Okay, and so that's kind of the first big thing. Then let's talk about, we can kind of break this up. They give us three things: calories, vitamin A, and vitamin C. And so we're going to take each portion. I know that I want at least 300 calories total, where X gives me 60 and Y gives me 60. So we're going to start with an equation that says 60 calories of X plus 60 calories of Y has to be at least 300 calories. And I'm just going to put a little note so when we look back later we know what we're talking about. So that's the first thing. Okay, then let's do vitamin A. 36 units of vitamin A is what I have to have. There are 12 vitamin A's in drink X and 6 vitamin A's in drink Y. Okay, so 12 units of vitamin A in X plus 6 units of vitamin A in Y has to be at least 36 units. So this is vitamin A. What's our last one? Vitamin C. Okay, vitamin C, let's see how much. We have to have 90 units total, 10 units in X, and 30 units in Y. So 10 in X, 30 in Y has to be at least 90 units of vitamin C. Okay, now we got a little bit of rewriting to do, and you can take the time to do that if you'd like, but here's how it works out. For calories, if we rewrite this, we get Y is greater than negative X plus 5. For vitamin A, if we rewrite this, we get y is greater than or equal to negative 2x plus 6. And for vitamin C, when we rewrite this, y is greater than or equal to negative 1/3 x plus 3. All right, it's coloring time. I am going to follow the same way. These two are going to be in yellow. Okay, so here's one edge, here's another edge, all of this in yellow. If you don't want to include that, that's okay with me too, because I understand that. All right, here we go. For calories, we got to go up to 5. 1, 2, 3, 4, 5. And my slope is negative 1. So I've got this line here. If I check 0, is 0 greater than or equal to 5? The answer is no. So we go away from the green line. All right, the second line, let's go 2x plus 6. So there's 5, 6. And I go down 2 and over 1, down 2 and over 1, down 2 and over 1, and I get this line. And I again am going to check 0. Is 0 greater than or equal to 6? The answer is no. So again, I'm kind of going away from that line. Last one, 1/3 x plus 3. So negative 1 over 3, negative 1 over 3, negative 1 over 3. And you get this line. If I check 0, is 0 greater than or equal to 3? The answer is no, so again I go away. Okay, so let me pull up my red again. Let's do some intersections. Let's figure out where this intersects. I know it's got to follow this line. And it looks like here's my ending point over here. I follow along this line until I get to the green. So I've got a vertex here and I've got a vertex here. It seems to follow the green then until I get to the blue, and then I follow the blue until I get to my y-axis. Okay, so I need to figure out the optimal cost. Now, when you think about this in terms, let's talk first about vertices, because I want to know if I want a maximum or a minimum. So I have a vertex 0, 6. I have a vertex 1, 4. I have a vertex 3, 2. And I have a vertex 9, 0. If I plug them into my cost function, which we said was 12 cents for x and 15 cents for y, here's what I get. I get 90 cents for the first one. I get 72 cents for the second vertex. I get 66 cents for the third vertex. And I get $1.08 for the fourth vertex. Now the question is, what is this actual question asking? How do I find the optimal cost and still meet the requirement? If I'm a company, I want to spend the least amount of money, but still meet whatever requirements people have to have. So the least amount of money means I want a minimum. So what it says is I need, for a minimal cost, my drink has to contain 3 cups of X drink and not 4, let's try this again, and 2 cups of the Y drink. So as you look at this, here's what we end with. You want to minimize the cost and still be able to provide whatever it's asking for. This is the type of question you would see on a quiz. We're asking you, again, this is the whole point of doing this coloring and programming and maximizing and minimizing. This is what people do, is they take a product and they want to minimize their cost while maximizing whatever idea they need in their product. And so this is 7.6. This is the end of chapter 7. Again, you will want multiple colors, but please, if you can, start the homework before you get to class.